Hey guys, I'm Nick, and in today's video we will be creating this kinda organic growth simulation, and there are a few tricks that I really wanted to share with you, so let's check it out. So here we are in Houdini, and you can see that we are rendering this with Redshift in Houdini. The base for our growth is just a simple free 3D model of rock, which looks like, let me uncheck this, which looks like this, something like this. I've got it from Turbo Squid, but yeah, basically you can use any sort of model here. And yeah, let's begin with a moss geometry, because we also have our rock there, and then I just copied it here because we should render out our moss as strands, as capsule strands. Here you can see it, and that's why we need to copy our actual rock to another geo node, which is rendered as your regular geometry. So let's go here and check it out what we actually have. So we start with importing our rock, and then I apply match size to basically make it a bit smaller. Target size is set to 555, and we are checking this scale to fit. Then we transform it. I just basically rotated it to my liking, so I wanted it to kind of like freeze in air, and just rotate it a bit, so we just have more detail that we see. And here you can see, if I enable smooth wire shaded, we can see that the wireframe is actually pretty good though, but I want a bit more detail. So what I did, and you could probably go with just a remesher, but to get even better results, I suggest going with a 1 remesh. And then if we have any like corrupted polygons, and that's more for 3D scans, because this setup is basically copied from my grains on bone or grain infection system. So basically you could go with just this remesh if your geometry is good enough, but just to be safe, I remesh it, apply VDB from polygons, then convert it back, and then remesh again. So now we see that all of the triangles are really the same size, and yeah, basically that's how you get your as clean as possible mesh. Then I add normals, and then I add 2 spheres with a mountain node added. Let me also remove these slides here. So how do you do that? Better if we enable it in viewports and uncheck enable it in viewports. Cool. So now let's go back to our moss, and here, yeah, you can see that those are your basic spheres, and add a mountain node to displace them. And then I create a point group, which in the left input we grab our normals, or basically our rock, and in the right input we grab our merge of 2 spheres with a mountain node, and bounding type should be set bounding object, group type obviously points. And if I enable that, you can see that here we have a selection of points. You can add them whatever you want, but I wanted it to not to be visible from the first frame, and then those moss pieces just like grow. Yeah, so that's why they're here. But this group is basically the starting point of our burning. What we need to do is grab our group and assign temperature attribute and assign value to 1. So basically these points here are already burning, and they are kind of like a starting point for our pyrosource spread simulation. Then we drop a pyrosource spread node, and here you can see, let me get it back. So we have a bunch of visualize options here. So I'm using burn, and basically that's the only thing that goes from 0 to 1. Or from 0 to actually 0.1, I think. Because we actually, and I know that I did it in previous tutorials, but we cannot probably go with the temperature. If we wanna, let's say, not only detect that the temperature is more than something, but basically for now, the temperature could be from where we are. Let me find the temperature. So right now it's from 0 to 1. If we go and let's play 39 frames, the temperature is from 185 till 342. So the range is always changing. And yeah, that's why we wanna sort of a constant attribute here. In the temperature change, I also wanted this simulation to run pretty quick. I mean, here you can see that it only takes 210 frames to actually burn this rock down. So cooling rate is set to 0, rate is set to 3, search rate is set to 1. For the noise type, for the diffusion rate noise type, I'm using periodic Berlin flow, element size 1. All the other things I think are default. I played with fractal a bit. Also for the fuel, played with the noise a bit. And for the combustion, I set the ignition temperature to 0.1, the burn rate to 0.3, temperature output to 0.1, and burn output to 0.1. And that gives me, you basically with these, you control how fast the actual flame or actual burn will spread. So here, if I change the visualize type to burn, you can see the pretty harsh indication where it's actually burned. So we will stick with this burn attribute, but I want this to be as smooth as possible because I want the smooth transition and smooth animation for our growing moss. So that's why I drop an attribute blur and I blur it 100 times. And here in the attributes we specify burn, and blurring iterations 100, step size set to 1. So that's how we actually can create something very smooth. Alright, so now we should remap a few attributes and of course scatter our points. So what I do here is I drop an attribute remap and here I remap burn to P scale. And actually here you can see that I'm not actually changing the range because burn goes from 0 to 0.1, and for the P scale I also want to go from 0 to 0.1. So you could see that we basically don't shift range here, but the main thing here is to use ramp. And you can see how smooth this ramp is, and it really helps to get this organic flow, organic growth thing. Because if this is linear, it's not like growing, it's like just spawning and animating the scale. So this is really crucial. And you can do that just by changing the interpolation to monotone cubic here and also here. So this ramp really adds just a touch that you obviously could notice if you don't do this ramp. So from here we go and add scatter. This time I'm using 2000 points, and then we go scatter align rotation. The node called scatter and align, and basically the only thing I am doing here is I switch the mode to add attributes to existing point cloud and rotation around normals. So you could do that in attribute wrangle or VOPs or something, but it's just easier to just spawn this node scatter align. And here you can see that min angle set to 0 and max angle set to 360. So we basically have 360 degrees variation in terms of rotation around normals. And then this one is also crucial. So here we drop another attribute remap, and original name is set to P scale and new name is set to time. And this is basically a retiming option for our growing moth. And I will explain this a bit later in details, but the main thing we need to do here is, here you can see that I created these L system moss things, and you can see here, it's, by the way, it's letter H on keyboard. So here you can see that it's a single L system with animated step size scale. I'm not animating the generations are set to 8 in this particular L system, and I'm animating the step size scale from 0 to 120. I added subdivisions and smooth node just so it looks a bit more like organic or something. And yeah, I made 3 of these L systems and I feed all of them into my copy to points. But before we do that, here in the P scale to time, we actually want to go with output max 4, because time is, in my case, it's 30 frames. So if we have our L system growing animation set to 120 frames, it's 4 seconds. And that's why we want to remap our P scale to time, and we want to remap in range from 0 to 4. And also super important here is to use that exact same very smooth ramp. If you go with linear, again, it will be more like a linear scale or something. So these ramps are actually super crucial. Here, by the way, let me remove the visualization, set it to none. And if I add color here and bind it to p-scale, p-scale is 0 to 0.1, so 0.1 here. And here you can see how the pyro affects our particles, our particle p-scale to be exact. So now what I want to do is add a bit of random to the p-scale. So if p-scale is more than 0, if it's more than nothing, I want to add a random number between 0 and 0.1 to the p-scale, so to the scale of our MOS. Here's a really basic expression, which is basically we get a random number based on point num, so it will be random for every point. And function rand, here you can see, creates a random number between 0 and 1 from a seed, so ptnum is our seed, and we will get any sort of number between 0 and 1. But we want to fit that number not from 0 and 1, but to 0 and 0.1. So that's why we are using this fit 0, 1 function. And then we add that to our p-scale. So then I want to colorize it, and this color will be passed to our MOS. So now to the fun part with alembics and actually copying them to points. You could see this setup in my RBD morphing tutorial. And basically what I do here, I bake these 3 alembics. They all are a bit different. I baked 120 frames for all of them. And then I just import them. So here you can see 3 inputs. I merge them all. And then I drop a connectivity node, and attribute should be class. And then I drop an attribute from pieces. So I plug the colorize node, like our last from this set of attributes and scatter line things. So I plug that into the left input of attribute from pieces, and to the right input from attribute from pieces, we plug our connectivity node. So it goes like this. And in attribute from pieces, we want to specify that piece attribute is class and mode should be random. Then we plug our connectivity to the left input of copy to points, and we plug our attribute from pieces to the copy to points right input. And here we have our beautiful MOS. But right now you can see that it is all in their kind of final, or not the final, but it is basically at the stage where it is on frame 90, but that's not totally correct because we bind our time to our p. So basically, when the p scale is 0, we want to start with this one, and when the p scale is 0.1, we want to be at this stage here. So we need to use prim intrinsic function. So obviously, because we are using alembics, we need to transfer our time variable, which we specified here in the p-scale to time attribute remap. We want to create an attribute promote node and select original name time, and original class should be points and new class should be primitive, so we can use it here in the attribute wrangle. And here in the attribute wrangle, here's the function. So set prim intrinsic, and we specify that we want to get our initial geometry. Then the parameter is ABC frame, then point number, and our time attribute. So this sets the value of a writable primitive intrinsic attribute, which is in this case is ABC or alembic frame. And this attribute wrangle should run over primitives. So here you can actually see what it is doing to our MOS. So where it's already burned, we have our, let me actually visualize this with the merge, so it's better to see. So here you can see that we have all these small particles, or not actually particles, but strands of our MOS here. But when it's burning, for example here, when it's like already 100% burned, we have our MOS in its final state. If you don't want these to appear here, you could always decrease the attribute blur, but I just wanted it to go like on more of the, on a bigger part of the rock's surface. So then I just converted back to polygon, because alembic is technically not a polygon. So then I dropped this out MOS, and basically our MOS setup is done. Now what I did for the actual rock, I just copied this and pasted it here in our rock. So you can see all that basic stuff that we had in the MOS geometry. And then I basically added labs auto UVs. Let me visualize that here. Then I actually removed the shop material paths, which was messing with the textures, and then I add null out rock. That's basically it for this setup. Now let's go and check out the materials. So obviously, yeah, materials, cameras, and lights. So I have this camera, which is just your regular Houdini camera. Resolution 1080 by 1920. A bit of depth of field and a bit of post effects, but I will show you that in a Redshift viewer. So for the lights, I'm using two lights. One is a huge backlight and one is kinda on top. Here, if I visualize it, it's here, and second one is from the backside. For the material network, and this one is pretty interesting. So for the moss, actual moss, we want to use a bit of subsurface and translucency here. So what I'm doing is using particle attribute lookup. So basically grabbing color from our particles and applying that as a diffuse color. But then I add a bit of green backlighting and flash translucency. Actually should be a bit more weight, but just a tiny bit. For the reflection, I'm using 0.362 for the roughness, and I think here it's all, but let's go and check subsurface multiple scattering. So the amount is set to 0.5 and we have 3 layers. Basically what I did, created the kind of sort of a color palette that I used here for these colors. I'm still learning Redshift, so if there's something that I did wrong, feel free to let me know, because in Octane it's a bit different to create all these subsurface scattering materials. And for the rock material, actually got a absolute color node set to very dark black green color. Then added a texture to the roughness, and actually I didn't knew that, but you should, for the normals and roughness maps and bump maps, obviously you should set the color space to be raw, and then it will be working correctly. And here for the normals, got my normals and plug that into bump map, set the input map type to tangent space normal, and then plug that into the bump input of our material. So now let's fire up render and I'll show you what it looks like. So here it is. And because of this subsurface scattering, I actually ended up using very large sample count. I think it's between 1000 and 2000 samples, but actually I really like how it turned out. So yep, you can use any geometry instead of L system. It's basically this remap thing with alembics, which I think is pretty dope. So yep, that's it for today, guys. Thanks so much for supporting me here on Patreon. You all are awesome people, and your support allows me to create these tutorials. There will be much more in the future, so definitely stay tuned, and I'll see you next week. Bye!